Okay, so we are very happy to have Barton to inaugurate this first talk of the series of the String Field Theory Journal Club. And he will speak on non-local field theory, rolling tachyons, and the initial value problem. And thanks again, Barton, for agreeing to give the talk, and you can start.
Right. Well, I guess good morning, good afternoon, and good evening to all of you. Thanks for coming, and thanks for the invitation to give a talk on this forum. I think it could work out to be a nice thing for the community. So we're definitely should be grateful to the organizers for providing this ability to stay in contact and share some ideas. All right, so I will just get started. Given, I'm happy to take questions as we go along, and I've prepared a talk that probably would be given at a leisurely pace in about an hour and 10 minutes. So if it lasts a little longer than that, that's okay, but I will indeed stop at the right time. That for us in Boston is 10:30 a.m. So that's the title of my talk shown there, non-local field theory, rolling tachyons and initial value problem. And the motivation to get going with such a set of questions was in a faraway distance, was a black hole information puzzle, and all this talk about non-locality helping to resolve the way that information gets out of a black hole, and some hints at the non-locality of string theory or string field theory could play a role. And we won't have anything to say really about that question, but that was the motivation to look back at these issues and see if we could say something new. Now, this is a complicated subject full of puzzles and claims and conventional wisdom, and we don't know how much of it is really true. But we decided to work on it and to apply some ideas that were used recently on similar problems to see if we could say something new. So here's what this work is about. In fact, it's a collaboration with one of the organizers who's happily here at MIT, Harold Irvin, who just introduced me, and with a graduate student at MIT, Atakan Hilmi Firat. This is a paper in preparation. Atakan Firat did speak about this a few weeks ago in a string conference, and some of you were here. And we've been working on it, and we're about to finish the paper, and hopefully it will be finished sometime next week. And we're looking forward to any comments or questions that will appear today, and see how to proceed. So this talk will go as follows, have 4 parts. I will begin by introducing the issues and the model. Then I will talk about redefining the time-dependent theory. It's a non-local theory that we're going to look at, and we're going to focus on the time-dependent theory and try to see how this non-locality can be done away with, largely. Then we'll consider the same thing for the general non-local theory that is not just time-dependent. And this non-local theory has to do with tachyons. So in the light of the results in part 2 and part 3, we re-examine rolling tachyons and try to say something new about this. Now, there's a lot of references. They will appear in the paper. I haven't gotten the time to put too many references in here. And I will mention some of the works, but many of you have worked on these problems for a long time, and we hope we're going to be citing your papers and we're not forgetting them or unaware of them. So let's begin with the issues and the model that we're going to work with. So it is a fact that string field theories display a number of non-localities. There are higher derivative theories, and they're written in a way that these non-localities are quite apparent. Indeed, the Lorentz covariant formulations make this clear that we have non-localities both in time and in space. So at least formally, you write an action and, there are higher derivatives in both time and in space. So these non-localities play apparently an important role, and they're part of the argument that one can make, and was made particularly more precise by Ashok Sen and Roger Pius on the absence of UV divergences in Euclidean space. So while in general, a theory with non-localities, spatial non-localities are somewhat familiar, perhaps also in non-commutative field theory, time non-localities are usually considered that are problematic. And one way is to see that is that it's difficult to formulate an initial value problem because apparently you need to, if you have a differential equation and in time and you want to evolve a configuration, if it has infinitely many derivatives, you need infinitely many initial conditions. Well, that's clear when you have finitely many time derivatives. But when you have infinitely many time derivatives, funny things happen. But nevertheless, without a good initial value problem, you cannot predict future evolution with confidence. And that's a lack of predictability. And in addition, when you have non-localities in time and in space, there can be violations of causality and unitarity. So all kinds of possible problems can be there. So there's an obvious question, which is if we can reformulate a non-local theory in a way that it makes it clear that there is an initial value problem. So that is a possibility for a theory with infinitely many derivatives, where somehow people find out that there seems to be just very few things you can do to fix a solution, initial conditions expressed in unusual ways, and therefore you look for a formulation that you could have an initial value problem. Well, certainly for string field theory, that formulation, although a little bit singular in some cases, is the light string field theory. There's time derivatives. This is ddx plus, or dd tau, x plus and tau. In the kinetic term appears this first order time derivative, and the time derivative doesn't appear in interactions at all. So this is a theory that can be evolved in conventional ways in time. So people have wondered, because people could formulate the covariant string field theory and formulate the light string field theory independently about the relation between these field theories. And that has been many people and many authors over the years working on this problem. And finally, there's a more complete analysis. One could say the relationship between these two string field theories has largely been established by Erler and Matsunaga. So on the other hand, there's also very old paper of Eliezer and Woodard that criticized string theory and string field theory in that these higher derivatives cause enormous number of complications. And in fact, their viewpoint is that light-cone string field theory filters out nonsensical solutions of the covariant string field theory. And these theories are only equivalent in perturbation theory. The S matrices are the same, but the covariant string field theory could have solutions that the light-cone string field theory just doesn't see. Well, there's some solutions that the light-cone string field theory doesn't see very well, but that is relatively understood. Those are light tachyon condensation problems, static tachyon condensations, because those are configurations with zero momentum, and light-cone string field theory with zero momentum is very singular. So anyway, those issues, to some degree have not been analyzed, and they're not too precise, but one should also say that in some ways violations of causality or things like that have not been seen in string theory. On the other hand, before we are just too confident that things should work out, I would say that in some way, the open string field theory has rolling tachyon solutions that seem somewhat close to nonsensical at first sight, for sure, and they're not clearly understood. Ever since this was analyzed a long time, and some of that was work I did with Nicholas Moller long ago, and that was followed by lots of nice works by Hatta and Fujita, then by Schnabel, by Elwood, by Hellerman and Schnabel. There's recent work of Erler, Matsuda, and Schnabel as well on these problems of tachyon rolling. But at least if you take naively the simplest rolling tachyon solutions that you could have, the tachyon potential is like that in the open string field theory. The tachyon, instead of rolling and kind of settling here in the tachyon vacuum, seems to do very strange oscillations in which it goes down and then goes up and overshoots and then comes back and goes down and then starts oscillating in rather strange ways. And in fact, there's no evidence that the final state of this system is the so-called tachyon matter discussed by Ashok Sen with zero pressure. So there it is. It seems to be a solution of open string field theory, and its interpretation has not been clear. Its status has been confusing. And if you want to be a little pessimistic, you could say it represents one of those solutions that maybe the theory shouldn't have, or it's doing something unphysical there. So there are some options of what could be happening here. One is that despite the current absence of evidence, this rolling tachyon solution is describing tachyon matter in some very complicated way. The other possibility is that this rolling tachyon does represent a different but consistent solution. Not quite tachyon matter, but something we haven't exactly thought about. This rolling solution may or may not define a boundary conformal field theory. For tachyon matter, there's a boundary conformal field theory, but for this solution, we don't know what it is, if it is something. Or it could be that this rolling solution is unphysical, and it's one of these solutions that the higher derivative theory might have that really should not be part of the theory. We certainly hope that's not the case, but given the puzzles, we just should consider that possibility. So let us introduce the model that we have, and we'll try to explain what we're going to do. So the model is a non-local field theory that we have a tachyon. So as you can see here, there's a tachyon field with the standard mass. We use the usual metric, which is mostly space-like. And the derivatives follow this notation. And if you consider the open string field theory Lagrangian truncated, just simply truncated, it's not an effective action for the tachyon, it's the truncation of the conventional width and open string field theory to the tachyon field. That's how it looks, a kinetic term and a cubic interaction with non-local factors up there, and controlled by a constant gamma that appears to control also level expansion. So there's an amount of non-locality characterized by this number gamma, because it's the way the exponentials work there. To get rid of units, it's actually quite convenient to get rid of units. We scale the derivatives, and then the action becomes simply of this form. And we'll call this number that appears here and multiplies the Laplacian operator, we'll call it the non-locality parameter Xi. And in this case, the value of the non-locality parameter is 0.26. That's the number that appears in string field theory, in covariant open string field theory. What is that? It's a measure of how non-local the theory is. Alternatively, that's a unit-free number, and it's a product of the mass of the particle times the scale of the non-locality, or the scale of the non-locality divided by the Compton length of the particle. So it's a pure number that quantifies the non-locality, and it's associated to a length scale once you have the mass scale. So if you generalize this, still working with a tachyon, you would write a Lagrangian that has all these constants here, a mass squared, a coupling constant, length scale here. And well, you can scale coordinates, you can scale fields, and you can scale the Lagrangian. And for our analysis that will be essentially classical field theory, it doesn't matter. So you can put them back or take them out as you wish, but this is a canonical simple form of the action, in which by the time you're unit free, you appreciate that the non-locality parameter is basically the main thing. So rather than all the work that has been done in p-adic models, and all these models works with this Xi squared being a number, as we said, for open string field theory, 0.26, we will treat Xi as a parameter. So we will only fix it in particular circumstances to do things. But if we have a parameter, we have better analytic control, and we can ask questions as the deformation of the local theory into a non-local theory by turning on Xi. So rather than having two theories, the local and the non-local one, we have a continuous deformation, and we may understand better what's going on. So we can explore both large and small non-locality. Then a chi-squared expansion of the theory is a derivative expansion of the theory. And we will work in the framework of, as you would do with an effective field theory, where you keep more and more terms, but try to make sense of the theory at every stage with more and more interactions. It's fun to get what that number exactly is for the p-adic strings, and if you define it similarly for p-adic strings, chi-squared depends on the prime number p of the p-adic strings, and it's given by 1/4 log p. The p-adic string with p equal 2 is the most similar to open string field theory. It has a somewhat lower value of the non-locality, is 0.17, but the non-locality increases with the p. All right. So a couple more things before we finish this introduction and things like that is here is the model again in front of you, and there's a conventional wisdom that has been said and kind of assumed that you can eliminate the non-locality in perturbation theory, and what we find is that the reality is that it's a lot more nuanced, it's more subtle and more interesting. It's not quite so obvious when you really have to do it that you can remove the non-locality, and we'll see what really happens. So it's an exercise in effective field theory, basically what we're going to do. And as in effective field theory, or more generally in theories without care of space-time topology, at least we'll do that for the time being, we will ignore total derivatives in the Lagrangian. So we will not focus on total derivatives. They don't affect equations of motion, and in principle don't affect the dynamics, although there will be a very curious twist on that. Okay, so I finished essentially my introduction. So I'll continue if there's no particular questions, but if there are any questions, please go ahead.
Yes, one point. I have given a bachelor thesis on higher derivatives to a student. In particular, there is a paper by Woodard, the people you quoted before, about the fact that when you do higher derivatives, you have to be very careful about forgetting boundary terms, because if you are forgetting boundary terms, you are actually eliminating higher derivatives. This is his claim in one of his papers. And okay, this was just a point. I would like to hear what you think about.
Okay, we'll see some role that is a little surprising for higher derivatives, as you will see. But you know, at least naively, just if you're in a space-time that is infinite and fields configurations are reasonable, these higher derivatives shouldn't have any effect. But we will see something curious about them, so maybe it has some relation.
Okay. Barton, can I? Sorry.
Yes.
When you say that you can remove non-locality in perturbation theory, as far as I understand, you can remove interaction if you allow non-locality. Is this a different thing? You can just, if you allow to divide by to introduce propagator and interaction, then in principle you can remove.
Well, we're going to be doing redefinitions that are at every order local, and we will be removing the non-locality step by step, as you will see. So, but we will always be preserving, in the sense of effective field theory, the S matrix of the theory. So the S matrix of the theory is beyond, I think, suspicion that we're going to be preserving it. But whether we do something non-perturbatively changing the theory is a lot less clear. Okay, so let's begin with our claim of redefining the time-dependent theory. To me, at least, this was a little striking, and I think, as you will see, it's a result that is almost, in some way, a little too strong and puzzling. But we'll see, and we'll discuss it. So first, defining a few terms, terminology. We call a higher derivative something that appears when you have two or more derivatives acting on a single field. So a higher derivative is something when you see d squared or d cubed acting on a field. A higher derivative term for us will be one where there is at least one higher derivative after you try to eliminate it by making use of integration by parts. So, so for example, there it is here. This term, d squared phi, is a higher derivative. Now, this kinetic term is not a higher derivative term because you can write it with first derivatives by integration by parts. On the other hand, here you have a cubic term. You have a cubic term, and this cubic term has four derivatives. However you integrate it by parts, there has to be at least one field with more than one derivative. So this is definitely a higher derivative term. So these are the terms that we will try to get rid of. So we will focus now on the theory with just time dependence. So the Lagrangian now becomes this one. There's the exponentials now have just the time dependence and the kinetic term. So our claim number one is that all higher derivative terms in L can be removed by field redefinitions in an expansion in psi squared. So higher derivative terms go away. But our claim is even stronger. Any term in defective field theory that has first derivatives of the field, here it is, a phi dot, and this to the power n times some power of phi. This is not a higher derivative term because it's just first derivatives on any field, but it's a term with lots of derivatives, and those also can be eliminated. So at the end of the day, we claim that the redefined Lagrangian has a canonical kinetic term and a psi squared dependent potential. And by canonical kinetic term, I mean something like this, the standard kinetic term. And this turns out becomes a potential. So that's a claim. I'm not going to do the proof, but I'm going to sketch it and give you enough insight. It's not very complicated. So let's do the first step. Suppose you want to redefine this Lagrangian and remove the derivatives that appear there. So you first expand the Lagrangian in a series expansion in psi squared. So there's L0, the theory with psi squared equals 0, then the first term. And here they are, L0 is here. And it has a potential consisting of the mass term and the cubic interaction. And there is here an L2. As it turns out, this term is not the higher derivative, but it would be some sort of, if you integrate by parts the dt, you would have first derivative. So you could decide to keep it because it's not an offending higher derivative. But of course, it would be simpler if you didn't have it. It has it has two derivatives with respect to time. It's a cubic term, of course. And we'll try to get rid of it in order to find just a canonical kinetic term that we can analyze in a simple way and a potential. So we do a field redefinition that to this order is just of order psi squared. So how does the Lagrangian change? The Lagrangian is the first one, plus to order psi squared is linear in the field redefinition times the equation of motion. And then we have the term psi squared L2 that we had here. It's just copied here. So in order to cancel the higher derivatives, this term and this term, we can choose delta 1 to be minus phi squared. And all it does at the end of the day is cancel these derivatives and give you this term minus psi squared times v prime here. So the extra term is this one, psi squared times phi squared times v prime. And as you can see, this is the derivative of the potential with respect to its argument. So this is non-derivative. This is just a potential. Indeed, v prime of phi is phi plus phi squared minus phi squared. And so it's a simple thing. And the Lagrangian acquires a psi squared term in the cubic part of the potential and a psi squared term in the quartic part. So we still get a standard kinetic term plus a potential that is the original one plus modifications of order psi squared. So this can be done to first order. The idea is that there's an induction hypothesis that after some redefinitions, the Lagrangian has been put in the form of the zeroth plus a potential, as we did with order psi squared, plus potentials to all orders up to some psi 2k that has lots of derivatives, and we want to get rid of and convert into something that has no derivatives. So we want to show that we can remove those derivatives in L prime 2k. For that, we'll do a field redefinition of order psi 2k, so that the new Lagrangian after the field redefinition is the original one. And to order psi to the 2k, that we have it here, only the linearized part of the redefinition matters, and everything else is higher order. So you...
Barton, I have one question.
Yes?
Yeah. So how important was it that the structure of the initial Lagrangian was what you started? For example, if we start with a, say, tachyon dBi action, could one still do this redefinition and bring it into the standard form?
It does, you know, in some theories, if you have a dBi action, that we found it a little complicated to do these redefinitions. They could be done, but it was not natural. We didn't have a nice place to put the non-locality parameter and controlled expansion. That was one thing. And So it's very important what you call the non-locality parameter, because it affects what the L0 is. And if you have a definition of the non-locality parameter, when you set it to 0, you identify L0, and the redefinitions get affected by the L0 all the time, because you work to eliminate in that order. So actually, for people that are interested, we did have trouble defining a way the DBI action, and part of that was also that the DBI action doesn't have higher derivatives in that sense. It's also like first derivatives on fields. So somehow, also for the p-adic string, actually, the procedure is a little less clear how you should proceed. So we also found it a little difficult to identify the chi-squared properly in those theories. So so it may not be completely general. Certainly for any scalar field theory with any potential, it should be no problem. And at least happily in the string field theory, it goes like that.
I see.
But then you'll lose.
Have used, for example, the number of derivatives. Let's suppose that we have only time dependent.
Yeah.
Square root of 1 plus t dot square, right? Something like some potential v of t times square root of 1 plus t dot square. And you could, yeah, 1 minus t dot square. So you could have expanded it out in powers of t dot and put a xi parameter depending on how many powers you have.
If you have a psi parameter, if you put it kind of here or something like that.
Let's say,
yeah, we had this theory is a little complicated because so if you would have maybe I think a v of t, then like a minus psi squared v of t times t dot squared. So the theory with psi squared equals 0 doesn't allow you to remove higher derivatives. It just has too trivial of an equation. So you already have to, there's no L0 that has the ability to take away derivatives like we did it here.
I see.
So what we tried was to put this and maybe put a 1 over xi squared here. And then you have a 1 over xi squared and things like that. We found it a little difficult actually and fairly intractable in several ways. But I could not say there's no clever way to do it, but we just kind of stumble with it and nothing seemed to make much sense. And then if you start redefining things with psi squared already there at zeroth order, sort of the expansion doesn't work well. Inverse powers of psi squared start appearing and everything gets very complicated. So so there might be an interesting a way to do this, but we certainly don't know very well how to do it.
Sorry, but the action you wrote is not actually higher derivatives, because if you compute the equation of motion, you get at the most t double dot with t with two derivatives.
Right.
So it is not actually higher derivatives.
Yes, exactly. But as we will see here, in the scalar field theory that we had, even those derivatives that are not higher derivatives, we could get rid of. So there's an idea that this maybe could be done, and I think would be worthwhile. Okay.
So just if I can add a comment for Ashok. So one case where, so what we have seen where we get trouble, in fact, it's when at the lowest order, so without psi square, if we need to have something with derivative and without derivative. So like if you get different power of psi square for the derivatives and for the potential, for example, then it's where we get troubles. So like for this dBi action or p-adic, it's a case where the derivatives naturally come with the parameter. And in that case, we didn't find a nice way to do this procedure.
I see.
Okay.
Thank
you. Sure. Thanks for the question. So what do you need? Should I erase those things? No. I can erase this one. Okay. So in order, let me go back here. In order to eliminate higher derivatives, you see that you need to factor a second time derivative of the field. So we need that any term that appears in L prime to K with derivatives can be written, so x to K must be written as d squared phi times that. Then you can choose a delta 2K to kill this term. And the result is that the d2k is replaced by minus v prime of phi. And you have now a term with two derivatives less. If x0 still has derivatives, this whole term must be possible to write in this way, and then you should go on and on. So the whole question hinges on being able to write terms up to total derivatives with a factor of d2k in front of it. So here is the sketch of the proof. A general term in x2k is written in this way. It's a product of terms with higher derivatives. Here they are. I will 1, 2, 3. There are L of them, K1, K2, up to KL. All these Ks are 3 or more, because if one of them was a D2K, a D2 phi, by the argument before, you can immediately eliminate it. You don't have to work anything. You can eliminate it if there's a D2K factor. So all this term has terms with Ks that go higher than 3, and they're ordered. And then you have first derivatives and terms without derivatives. So this is the general term you can produce, and we want to show it can be eliminated. We call T, this here, this term T, a term of index L, because it has L factors with 3 or more derivatives. And we call K1 the lowest order of T, which is the lowest higher derivative that appears here. So the claim is that if you integrate by parts on this term with the least number of derivatives, you integrate by parts at time, you actually don't change the index of this term, because this lowers by 1. Then when the derivatives act here, you know, these are separate factors. When the derivatives act here, they produce a second derivative that can be eliminated. Here it produces a first derivative. So the terms just keep the same index, but the lowest order goes down. So the lowest order, you can keep it down, down, down until it becomes 3, and then it becomes 2, and then you can eliminate it. And then the index goes down because you have one less factor. And then you proceed like that until at the end of the day, you have a term with just these things, first derivatives and powers of fields. In this case, by integration by parts, a first derivative and a couple of fields, you can integrate one of the first derivatives. Then it will give you things with another thing with first derivative that is proportional actually to the original term, and something with second derivatives that can be eliminated. So the result is that recursively you can replace this by actually something with 2 less derivatives and a factor of v prime and 1 more power on the field. So you reduce the number of derivatives, and since the number of derivatives must be even, you go down by 2s until you get to 0, and at the end of the day, you just have a potential. So we've done it here. Here is the action after we work on this. Mathematica program works well. Atakan and Harold had competing programs. I was doing things by hand up to a level, and eventually the errors were ironed out. And here is a form of the potential. Now, what we wish to have is an exact analytic form and understand the convergence and whether everything has been well defined or what happens, but we're not there yet. Although there's one important thing, the original potential has a critical point at phi star equal to -1 and at depth equal -1/6. And this potential, whatever the value of psi squared, has a critical point such that the minimum is also at -1/6. In a calculation like that, if you would be calculating this potential, the minimum and its value, and you have the potential like here to order psi to the 8, if you find the value of the potential at the minimum will be -1/6 plus order psi to the 10. That's how the result works out. I think after all, I'm not going too fast with the time, so I probably should speed up a little bit. The argument for the fact that the potential doesn't change its critical point is that, well, usually that's pretty physical, that point. But mathematically, the redefinition has parts that are derivative independent and parts that are derivative dependent. And actually, if you consider all the terms with derivatives and all the terms without derivatives in the action, these things don't mix too much. The variation of the kinetic term always produces terms, or not kinetic term, of all the terms that have derivatives, always produce things with derivatives. So at the end of the day, the new potential is just the variation of the potential relative to the non-derivative part. And V tilde is just some kind of redefinition of V, and redefinitions of potentials by redefining the field don't change the critical points. Don't change the depth of the critical points. So that's a good way to test your algebra as well. Okay, so here it is, quasi-symmetries and ambiguities. This is a very surprising thing that came up by accident because the programs for calculating the potential were giving different results. And we eventually found out that there's something a little strange happening. Is that in general, a field redefinition in a theory, if it changes the potential because it's phi going to phi squared plus phi cubed plus things like that, it would also change the derivative terms. But this doesn't necessarily happen for a non-local theory. We claim that there are field redefinitions that change the potential while leaving the kinetic term unchanged at linearized order. And actually, what happens is, as we will see, is that you change the potential and generate derivative terms at higher orders, so the potential is kind of changed irrevocably. So let me explain first what this is. So consider just an ordinary field theory. So this phenomenon happens for ordinary field theory, but it's not too useful there, maybe. And this we call a quasi-symmetry. And the effect is that if you calculate the first order variation forget about the second order. The first order variation is this times the equation of motion. And this product, there are 4 terms. The last term is a potential term. So it has no derivatives, but there are 3 terms with derivatives. They're here. And they all cancel each other or are total derivatives. So these terms are total derivatives, can be disposed away. And at the end of the day, the potential to linearize, the theory to linearize order changes only the potential. So with a potential like ours, and if you take a C1 of the form beta times psi to the 4, which is natural, the change in the Lagrangian is this one plus order psi to the 8. In a general non-local Lagrangian, there's this term, but then there are terms with order psi squared, psi fourth, like that. But when you vary something that already has a psi to the 4th on that Lagrangian, you still get this thing, and then order psi to the 6 terms that have derivatives. But you're already talking psi to the 6. So the potential to order psi to the 4th has been changed. That will change also the potential to higher orders, but already the psi to the 6th, the potential to order psi to the 4th has been changed. There's classes of quasi-symmetries. The next one is this one, has the same property, only the potential is changed to linearized order, and the general quasi-symmetry is this. And these quasi-symmetries can be put in this form, but I allow you to make choices of how you write the potential. So one choice, for example, that we explored was making the odd terms in the potential polynomials rather than non-polynomial. So that's a possible choice that can be implemented order by order with the quasi-symmetries. Again, this potential has the right minimum at the right place, so it's been tested. There's one more interesting thing about this, is that I won't get into detail, but given the question by Igor, is that these terms, these corrections to the potentials by quasi-symmetry also appear from total derivatives. If you add a total derivative to the action, a term of the form dt of dt phi cubed, this is a total derivative, and you ignore that it is a total derivative and use the algorithm to eliminate these total derivatives, you see some higher derivative terms here, and you just keep eliminating, then you produce these terms in the potential. So in some sense, this is an inbuilt ambiguity in that terms that are total derivatives that you could add to the action, if you process them, you ignore that it's a total derivative. You say, oh, this is 3 dt phi squared d2 phi, and then eliminate this by field redefinition and eliminate the others by field redefinition, you do get a potential. You don't get 0. So this problem has a very unusual symmetry, and we'll leave it there. Rather than going to the case of the rolling tachyons, let me consider the redefinition of the general non-local theory. We've done time, and we got a very surprising result. There's a claim that to imperturbation theory in psi squared, this theory is equivalent to a local theory, and we'll see what it has to do with rolling tachyons later.
Okay, so Barton,
yeah.
So these quasi-symmetries are symmetry, quasi-symmetries even for ordinary potential. Is that right? That you
Yeah,
can
for
ordinary scalar field.
any potentials. So far here is completely arbitrary.
I see. So if you take, for example, lambda 5 to the 4, you can convert it to something else by this without changing the kinetic term at all.
To first order. The kinetic term doesn't change to first order. So we just did the first order variation.
I see. So first order in the fluctuation.
Yes.
I see. Okay.
So it's I don't know. It would seem to me this should be known, and maybe it's been noted by many people before. But here it has an implication. In general, you would say, well, okay, you change the potential, but you've made interactions very complicated. But if you have a procedure to remove these higher derivatives, at the end of the day, you've changed the potential. So it's a little strange.
Yeah, I see.
Yeah, it's
Okay.
the fact that these three terms combine that guarantee that doesn't happen. And as I said, it has higher generalization. So there are infinite classes of them.
I see. Okay, thank you.
Sure. So now when you go to the general theory, you can say, okay, I'm going to try to eliminate derivatives, and maybe I should get ambitious and try to eliminate all higher order derivatives in the space-time dependent case. And we ask if that's possible. And surprisingly, you can go pretty far up to order xi to the 6th and eliminate all derivatives. But at xi to the 8th, you encounter an obstruction. And it's kind of interesting how it happens. And at that moment, you cannot eliminate all higher derivatives. And you have to make a choice. And we'll make a choice of removing all higher time derivatives, as we'll see shown now. So the variation of the zeroth order Lagrangian is this one. So this time you have, in order to eliminate a higher derivative term, you have to factor out a d squared phi. So if you want to eliminate the higher order derivative, this term better be possible to write as this way. So then by redefinition, it will become this. And with some luck, if this still has higher derivatives, you can do this and go on. So now here, not all terms with first order derivatives can be removed. This time for a space-time dependent thing, terms like this with two derivatives, two first order derivatives can be removed. But if you had four, it cannot. The index contractions prevent you from doing it, and you can't eliminate it. So here is how it goes. You write the Lagrangian again in powers of xi, and you start doing field redefinitions. And after you eliminate all you can, you encounter at 8th order this term. It has 4 fields and 2, 4, 6 derivatives. So it's not a term that was in the action at order xi to the 8th. A term that was in the action at original non-local action at order xi to the 8th would have had 8 derivatives. This term originates from the variation induced by the lower order derivatives on the action. So it just comes up, and that term we've tried for quite a while to write it as d squared. This cannot be written, so I'll write this here. This this term cannot be written as d squared phi times something. You try. We didn't write a proof of that, but it's simple enough that you try for a while and it seems completely clear. But and the terms could get worse at higher order. So it's not like there's just one abstraction. There are presumably abstractions at every order after this. So this is an abstraction. It is a higher derivative term because of this d squared here. That is acting on things to the right. So there are terms with 3 derivatives, terms with 2 derivatives. And the only way to do it is to try to eliminate higher order time derivatives with this term. So the abstraction is interesting. At the order at which appears, it's kind of interesting. And if you try to general classes of non-local field theories, probably there's a nice little problem of classifying all abstractions and all things like that. So anyway, it's kind of interesting also to show here this term, this d phi to the 4th, that is, you see, the corrections to the action to lowest order, to 4th order, and even to 6th order is mostly potentials as before. But here is for the first time that appears terms with derivatives that cannot be eliminated. This is not a higher order derivative term. This is not a higher derivative term because it's first derivatives, but it just cannot be eliminated covariantly. And perhaps it cannot be eliminated even non-covariantly. But in any case, it's there and doesn't ruin an initial value problem. It's perfectly okay. The problem is this red term. Anyway, here is how the theory looks after a little while.
Just a curiosity. Have you tried by introducing some auxiliary fields? Just, for example, the first term showed derivative of phi to the 4th. You could write it as derivative to the derivative of 5 squared times an auxiliary fields plus auxiliary field square. So I was, yes. And the same below. The question is, could you try to add some auxiliary field and play with them? Have you tried?
No, we have not tried. These terms are not problematic, so we can try that. I'm not sure exactly what we could do, but it would put the action in a somewhat simpler form, so it maybe it's nice to do it. Yeah. So here is the action, and the terms of this form that we were discussing now have psi 8 corrections. There's a term like this, and then this is all the non-covariant, non-Lorentz covariant part of the interaction after the field redefinitions. There's no higher time derivative, but there's a phi dot here. And here's the potential. And also I want to note that this term is exact. We saw the pattern, and this term is guaranteed to be this to preserve the on-shell value of the 3-point amplitude. This theory has the kinetic term, and there's no term here with derivatives that contributes to the 3-point function. So it should be the same 3-point function of the original theory on shell, and that's what you need. So here's a particular case where you can do these things. So this is the general theory, and we don't have a very elegant form for it, but maybe someday we'll understand it better. But certainly it has an initial value problem and a Hamiltonian can be written. I'll say things for a couple of minutes about light cone. Light cone is also possible to achieve a light cone formulation. There I show the Lagrangian and then writing the kinetic term using light cone coordinates, x plus, which is tau, x minus, and transverse coordinates. But the light cone theory for a scalar doesn't involve a gauge choice, but does involve field redefinitions, as we will see, finding the light cone. The interesting thing was that the attempt to remove non-locality eventually forces you to abandon Lorentz invariance. It's a very nice thing due to the obstructions. So the non-locality is somewhat robust. You can eliminate it in time, but then it kind of remains non-local in space, and light cone has the same thing. But it's particularly nice because in the light cone, the advantage is that the time derivative should only appear in the kinetic term, so it should be removed from the interaction. So the first term where the covariant analysis fails to do that is with L to the 6, where this term now is not an admissible light cone interaction because it's an interaction with time derivatives, tau derivatives, and that's not allowed. So we have to eliminate it. And I don't want to get into much detail because we don't have much time, but roughly the statement is that you, again, try to do this with the variation of the zeroth order action. You're going to try to cancel this term. And you write the zeroth order action in light cone. So basically, you have this d phi, which is this, and then you square it, and you have terms of this form. And the challenge is to eliminate terms that have tau derivatives. Any term with a tau derivative, this is okay in light cone. There's no tau derivative, but here there's a tau derivative, and here is a tau derivative. So just to give you a feeling of what you have to do is, suppose you have a tau derivative times x. You needed to write it in the form like this, d minus d tau phi, because that's what delta phi is multiplying with in order to eliminate this term. So what you do is you put 1 over d minus d tau phi, and this is light cone. 1 over d minus is the factors of 1 over p plus. You can't avoid that. And then you can integrate by parts this d minus, that is an inverse, that integrates again with a minus sign. And you put a 2, and you get this thing. So this term now, by redefinition, can be replaced by all of that. So you get this with a minus, and at the end you integrate by parts again. So the end result is a rule like this, that a d tau times phi times anything can be replaced by this times thing. So you have to argue that you can always do this, and we argue that, and we can get a light cone formulation. So this, to some degree, a more sophisticated version of this is what people that study gauge fixing to the light cone do. There's need to do a field redefinition, and that was featured in the work of Erler and Matsunaga. So, okay, back to rolling tachyons to conclude this talk and to give a little opinion on what is happening. So I think our analysis somehow sharpens a lot of the puzzles that have occurred with rolling tachyons, and well, I think they'll give us an opportunity perhaps to reach some conclusions about what that solution is and what are the issues with convergence on all this analysis, perturbative versus non-perturbative in Xi, several issues. So rolling tachyons, as known from the p-adic string theory, admit a series solution. Our model is not a p-adic model, it's a string field theory truncated model, but it admits the same kind of simple solution. It's a relatively simple thing to do. It is a series solution in exponentials with coefficients that can be determined recursively, but they are highly suppressed in psi squared. Following Hatta and Fujita and Schnabel and others, we find the large n behavior of the coefficients that it's partly experimental, partly analytic work. We have some confidence on this result, but they're certainly not mathematically rigorous. But if true, and all the evidence, numerical evidence and otherwise, is that they hold, means that this series for the rolling tachyon, it converges for any value of the time and for any psi greater than 0. This solution actually does not converge for psi equals 0. The local solution has a convergence, radius of convergence that goes up to the turning point. If you have a local theory, you're rolling here, the solution converges up to the point where you reach here, and it fails to converge afterwards for psi equals 0. But surprisingly, for psi different from 0, it converges. That has been argued in many ways, I think, also by other people. And the surprising thing, I think, is that it converges for any positive psi as well. So we have some control over the deformation of the problem. And again, these are the crazy oscillations. The turning point of this phi is at, in this zeroth order potential in the non-local theory is at -3/2. The minimum is at -1. And here is the -3/2 is the dashed line. The tachyon rolls and exceeds that turning point, then rolls forward into the bad region of the potential very far, and then turns around and goes negative and overshoots. And you can prove from the series solution that it's oscillating and each time grows. Not only it converges. So as I mentioned, the series expansion for psi equals 0 fails to converge after the tachyon reaches the turning point. But we found something nice, maybe ignored by some of us, certainly not quite realized. The rolling solution in the psi equals 0 potential is, can be solved exactly, and this phi 0 is how rolling happens. And it works for all times, and you can see as a series of e to the t has a radius of convergence, but it's well defined for all orders of t, and for large t, it goes back to 0. So this is the complete analytic solution for psi equals 0. And if you set up an expansion in psi for the whole differential equation, remarkably, each term can be found analytically. So this is the rolling tachyon solution as powers of psi squared, exact in time. And actually, you know, this is very nice, but in fact, the fact is that these coefficients are highly suppressed in psi squared, And if you write the series expansion of e to the minus 40 psi squared, you get terms that go gigantic, and only after about 40 terms or more, they start decreasing and eventually cancel each other to high precision to produce the calculation of B4. So if you have a calculation that needs B4 for the physical effect you're looking at, you need to go in psi squared to at least 50. And maybe 50 is not enough yet to do justice to this thing. So could be higher. So actually, not surprising, we saw in a paper of Schnabel and Hellerman saying things like, we went to order 5,000 in an expansion and use a program with 500 digits accuracy. So it's hard. Anyway, you can see here a graph of this differential equation psi squared expansion solution. The green is the local theory. The field rolls down and up. The blue, the red is the first, the first and second correction. The next one is psi to the 8. And you start seeing with the corrections that you overshoot the turning point. The turning point is that black line at minus 1.5. Here is the non-local theory solved by the series with the BNs. That's the red dashed line that has the oscillations, and solved with the differential equation. Is the same non-local theory, but with the differential equation solved to order psi to the 8. That's completely too little to see in the blue solution, the oscillations, the wild oscillations of the BN solution. So, but at any rate, you do see some things, and comparison, well, it certainly overshoots the minimum, that's already clear, and goes to the positive side quite high before finally returning. Presumably, if you go to psi to the 300, you will see the oscillations. And we'll see, that will have to wait. Here is the non-local theory redefined. That is the tachyon potential, how it looks afterwards. I don't remember, we'll have it in the paper, to what order of psi squared this was done. It could be psi squared to the 14th or something like that. The potential, you know, we were initially very afraid that the potential would be just going crazy, but the potential is quite regular for values of psi squared that we work with. So if you worry about radius of convergence in psi squared, some preliminary evidence that it's not so bad. It's probably okay. In this case, this potential, the turning point is at minus 127. So here is the turning point. Here is the value 0 of the potential. So the maximum is here. You're supposed to roll down here and turn back. Since you have a kinetic term that is canonical, that's going to be the rolling. There's no question about it. The turning point has been moved at minus 1.27. It used to be 1.5. At this order is 127. The depth of the potential is minus 1/6. That is as it should be. And so here it is. Here is an interesting comparison. On this potential, on the new weak side potential, you can do the rolling solution. You can do it not analytically, because it's a potential with all orders of phi and all orders of xi, but you fix xi and you can do, and that's what we call the numerical solution. There's no question that solution has to go here and do the standard thing of going back, up, and down. This is just the rolling in the new potential. On the other hand, there's the redefined solution. So you take the non-local theory solution, plug it into the field redefinition that took you to the canonical theory, and see what the canonical field should be. If everything works and is convergent and things, it should map the crazy rolling to some degree. It should map it to the conventional rolling in the new potential. And we find some evidence of that. You know, we cannot tell that the oscillations disappear because we don't have enough accuracy, because the only way to do this in a controllable way is with the differential equation in the xi squared expansion. So the one thing that was very interesting was that, if you remember, the non-local solution overshoots the turning point. The turning point now is at -127. And the redefined solution, certainly the redefinition corrects the overshooting. You know, remember, even the redefined solution overshoots the standard potential all the time. So here you have that the redefined solution actually turns exactly or very accurately at the turning point. So the redefinition corrects that and doesn't let it overshoot. It goes there. So it cures the first overshooting. It's not quite clear how much of the next ones it cures, but in principle, if things converge, it probably will cure everything. And it might work to all orders. So here is, again, another comparison, maybe, of this thing, and I'm coming to an end of the talk. So here you have the non-local theory rolling solution in red with psi equals 0.35. This is done with the BNs, the exponentials of NT. And you see the crazy oscillations, and it's quite convergent, and everything is good. The one point we show is in red. A red dashed line is the position of the tachyon vacuum. So the tachyon vacuum is the red dashed line, and it's kind of occurring, the field, the red field, is crossing the tachyon vacuum around this point. It just zooms by it. It doesn't stop to pay its respects to the tachyon vacuum or stay. It just goes through it and zooms away, unfortunately, or, well, that's part of the puzzle. And the blue dashed line is the redefined solution to order xi to the 8. So we take the series solution of the differential equation in powers of xi squared. That's our non-local solution expanded in powers of xi squared, calculated to powers of xi squared. And then we plug it into the field redefinition, and we find this curve, this blue dash curve. We found it kind of interesting that it crosses its own tachyon vacuum, which is the blue line, which corresponds to this point here, at about the same time that the non-local solution does. So both of them cross their tachyon vacuum more or less at the same time. If you're looking, you know, the redefinitions are a function of time, and there's perfectly good control about asking when this field is doing that, what is doing the other field is a well-defined question. Probably an off-shell question, but it's a precise question in this theory. And of course, in the redefined solution, you would expect no oscillations. The fact that there are no oscillations here is not convincing yet, because as we mentioned, psi to the 8 is just far too low for anything to show up clearly. So we probably are safe around here, but by this line, the blue line, that we wish this is the case, with the field redefinition not showing there. So the discussion, of course, is a standard one. The full rolling solution of the redefined potential goes back to the unstable vacuum. So goes from the unstable vacuum where there's a d-brane to the turning point, presumably no d-brane, and back at time equal infinity to a d-brane. So at least in the local version of the theory, it looks like a process of brane destruction or deconstruction and brane construction again, some kind of bosonic S-brane. But we don't know yet if this makes really complete sense. In the non-local version of the theory, it's not obvious you're returning to the same point. So precisely where the oscillations set in, our map, at least to this order of calculation, is not reliable, and we will have to wait to see what's happening. Is this rolling solution a BCFT? Could it actually be the tachyon matter hidden? But anyway, we just don't know, but there is some possibility that perhaps what we saw happening at the beginning with the redefined solution mapped by the non-local theory into standard rolling, perhaps after all, this is really brane dissipation and recreation is happening. So anyway, I'm done. I say one word. Full locality apparently can be achieved for the purely time-dependent situation. An initial value problem also can be done for general configurations at the cost of losing manifest Lorentz invariance. If this is true and these reformulations represent an equivalent version of the theory, our analysis suggests that the theory is causal. We wish to have closed form expressions for the potentials and understand them better. And a deeper investigation of causality in the original non-local theory is still warranted. The non-local version of the theory is the conventional string field theory that we all like. And it should be possible to argue that this theory doesn't have a causalitas or it's not sick directly. Of course, a manifestly clean formulation is useful, but perhaps there's a way to do this. And it has been called to our attention that there's a Bogolyubov causality condition that can be implemented in the path integral. Tom Bullis has been looking at that, and perhaps it can be used. If, after all, our redefinition to a local formulation, which is by inspection at least perturbatively causal, and if it's equivalent to the non-local theory, the latter must be causal. So without further ado, I thank you for your attention, and that's it.
Thanks a lot, Barton, for the talk. So what I say is that if you have time, we can take a few questions in case, and then I will just end the recording and we can continue to chat for people who have time. So do we have any question for Barton?
Yes, I have one. As usual, I have some questions. You have a look at Xi small. If you take Xi very big, consider the Xi very big, and you consider the simplex example where you consider only time derivatives. in this case, if you take psi very big, it means essentially that all the possible frequencies, if you move to, if you use Fourier analysis, all the possible frequencies are free, but the constant one, the frequency equal to 0. In that case, you get only the potential for the constant time constant mode, which is exactly a kind of vacuum. So the point is, if you consider psi very big, and not exactly infinity, it means essentially that you are just allowing very small frequencies, and this is reasonably reproduced by a very shallow potential. So if you look to things in this way, it is reasonable that you have both a kind of causality and an equivalent theory with the usual number of derivatives. So have you thought about a very big psi?
You know, I don't think we've thought much about large psi squared, but I agree with what you're saying. In Fourier space, those modes would be made essentially free, and so you would have a free theory for all these Fourier components, and the conventional kind of theory, a potential for the zero mode. So so the theory may not be so exotic after all at psi going to infinity. I'm not sure. We did a little analysis of causality in this work, and there was nothing particularly singular about the psi going to infinity limited, if I recall well. You know, the particles just propagate in funny ways, and so short answer is I just don't know of any strange thing happening for you know, if you look at the dispersion relation, so the quadratic theory, and around the minimum of the potential, if you look on the physical theory, you have a tachyon, and if you look at the bottom of the potential, it has a mass squared that is positive, because you're at the bottom of the potential in this model. This is without non-locality. What we found, I think, is that with a large amount of non-locality, if I remember right, the mass squared, the effective mass squared at the tachyon vacuum became negative, tachyonic again. So, so it was a little surprising, but you know, it's a good question trying to understand that limit. That probably is a very interesting limit. I don't know if my collaborators, Harold or Atakan, want to say something. They remember any particular result?
Yeah, so indeed, like when we looked at the dispersion relation and effective mass, like in the infinite non-locality limit, you just kind of go towards some nice theory. So in particular for the tachyon, so the tachyon you start in the unstable vacuum when we did the analysis, and it's kind of shifting it to a stable vacuum. So you're exchanging tachyonic and non-tachyonic masses in the infinite non-locality limit. But we like it doesn't look there is anything special going on. It just becomes simple for dispersion relations.
Carlo, maybe for a question.
Yeah. Hello. Hi. Can I ask a question? Hi, Barton.
Oh.
Hi. have you thought about essentially what I understood is that your logic is starting with the Witten open string field theory and taking, let's say, the level 0 approximation to the tachyon potential and then study this as a field theory. So
Right.
what would happen if you would try to integrate out some massive fields from Witten theory and ending up with a tachyon theory that is not just cubic but quartic and quintic, etc., etc.? Would you get the same results, or would the psi parameter would somehow change?
I don't think the psi parameter would change because it's defined by the cubic coupling of the tachyon. So that will not receive, I think, contributions from other things. On the other hand, I think we don't know, but there is something very funny. When we go to the Lightcon in this procedure, this recursive procedure for that field theory, we're going to get a totally non-polynomial theory. And somehow when you're in string theory, when you go to the Lightcon, it stops at tachyon to the fourth, or the whole action stops at tachyon to the fourth. So certainly, there is some level at which the massive fields make a big difference. On the other hand, when you look at the rolling solutions in the string field theory, actually, we've done that, and we did it with Muller, and it was based on suggestions that Ashok had of using the lump solutions to use to do this calculation. And then we found, in fact, that was the surprising result, that if you do the rolling of the tachyon, is extremely similar to the rolling we've done here. And the massive fields also start doing things with more and more oscillations and don't seem to do change the nature of the solution much. So that solution is based on Cauchy's and actually exhibits a very analogous type of oscillations. Oh, it's so analogous. Even the parameters seem to work out to be, the scope of the oscillations is very comparable. So I think we probably can learn good stuff from these models, because certainly this model versus the rolling problem in the string field theory has not been very different so far. Nobody has found any significant difference.
Perhaps following these things you are saying about solutions for rolling tachyons in open string field theory. So recently with TED, we analyzed with our solution precisely this Cauchy deformation. And we also observed precisely these oscillations.
Right. Okay.
So it's probably something very universal.
Yeah, it seems to be there, and I think it would be time to really understand what's happening. Just been around too long, and we have a very strange claim, in a sense. The fact that we claim that we can make the time theory local means that we claim, or our results claim, that this crazy oscillations is what the non-local field does when the local version, the good dynamical variable, is approaching back the top of the potential.
But you see what we found out with TED is that, in fact, let's say the worldsheet origin of this oscillation is, at the end of the day, just contained in the 3-point function of let's say one plane wave and 2 boundary condition changing operators describing this Cauchy deformation. So it's really the 3-point function that has so when you do the Fourier transformation of the 3-point function, you go from momentum space to, let's say, position space. Then you see these oscillations.
Right.
They really come from conformal field theory.
Yeah, but by the time somehow they turn into observables, that's the part that we apparently can't do very well, because any attempt to calculate the pressure of these rolling solutions has given ever-growing oscillations of the pressure as well, which is not consistent with tachyon matter and not quite consistent with going back to the unstable Debring. So either the calculation of observables for these solutions is just totally inadequate and incorrect, or there's something wrong with the solutions, or
Yeah, but we have ways to compute the boundary state, right, from the string field theory solutions.
right. So I don't know of anyone that has done that for this rolling solution and found any clear result, or if there is, we would like to know.
I think that at least formally, with our solution, we can show that the boundary state is the BCFT boundary state. And
I think we did. I think we did.
Is known, as far as I know. So,
Barton?
Right?
Yeah, I think we did. We did in our paper with Michael.
So which paper is that, Eugene?
Boundaries state construction of our paper. So if you use a rolling tachyon solution, and I think we analytically proved that the boundary state can be reproduced. So
yes, you did in the first paper of the boundary state, I remember.
Yeah, that's
yeah. But that was this rolling tachyon, the one, not the Koch, but the e to the minus x naught.
That's right. Yeah. So we assume the regular marginal deformation.
Yeah. But I think that even for the Koch, you get similar. You can show that the boundary state is reproduced. So you have to use this other method to build the boundary state. This one that Martin and I and Mathieu did. But essentially, you get the BCFT results, and so you find the vanishing pressure at the end, I think.
Well, but any attempt to find the vanishing pressure in the field theory limits has not worked so far. So
yeah, okay.
So
that is
so again, Yuji or Carlo, which papers have this? Was that something I was there too, or not?
Yeah, you were there.
With Kiermaier as well, is that right?
That's right.
Yeah, the Kiermaier. Yeah, I somehow okay. So the mystery is kind of you claim at the level of the field theory only.
So I think it is essential to include all the massive levels to reproduce the boundary state. So, so my impression is that we can see the regular physics in the crossing channel, but if we want to describe in terms of open string channel, it can be wild things. So that was my impression.
If you describe what?
So the something regular in the cross string channel can be very wild in open string channel. That's what the kind of impression I got from the analysis. So, but if we include all the fields in the open string channel, there can be somehow miraculously reproduce the cross string regular. So in the cross string channel, the time evolution is fairly regular. It's the boundary state discussed by Ashok, right? But in the open string channel, it's very wild. But then all the massive fields can play, so they all play a role to reproduce the regular physics in the cross channel. That's yeah.
That's the
Yeah,
intuition.
I think this is CFT, right? The CFT is telling you this. So it's the 3-point function in the three open strings has some profile in space, but the closed string against the boundary state is a different profile, and the oscillation are just going. Yeah, so it's a. So that's why I would say it's just CFT in a sense. It's a CFT effect.
Yeah, I agree.
I see.
So somehow string field theory is adding some decoration to it, but the skeleton is just CFT.
Was there a difference between the Koch type solutions and the e to the nx solutions?
So the Koch are symmetric in time. The profiles that we analyzed are symmetric in time, of course, and while the e to the x naught are not symmetric in time. So you see oscillations only on one side with the e to the x naught, if I remember. But this was computed by Yuji and some other person, I think, for a classical solution of string field theory, right, Yuji? I think.
Sorry, which?
So you had this KOS solution, right, where you computed the profile of the Rolling Tachyon for the e to the x naught solution.
Yes.
Analytically, and then so this was for the e to the x naught, and this solution is oscillation, let's say, only for infinite time, if I remember correctly. While the Koch deformation, I think the only analytic solution that somehow got close to get sort of finite results, and this was this last solution we had with Ted, where we computed the tachyon coefficients of the solution for the Koch marginal deformation, and we saw this oscillation that are symmetric in time. So you have a wild oscillation in minus infinity and plus infinity also.
Right.
That's my recollection.
I see.
But then, okay, then if you compute the boundary state from the solution, then you get the BCFT boundary state.
I see. So in that respect, it would seem to me a little unclear then what the redefinition to the canonical theory is trying to tell you. So maybe this is perfectly okay for the tachyon model, but it's either just doesn't tell you much of the physics of the open string completely. It would be a case where the rest of the fields play a very important role, but it does seem like if you accept that you can map this to local dynamics by doing the kind of redefinitions we do to go to the Lightcon as well, the potential becomes conventional apparently, and you seek to roll down and back up. But that's not what the boundary state is telling you.
Yeah. But perhaps, okay, maybe this just, but perhaps if you would include all the let's say higher point correction you get by integrating out the massive fields, so that you don't just get this non-locality, but you get also a non-polynomiality.
Right.
Then these two things combined would do something.
I see. Yeah.
I don't know. There's just maybe that could be a possible way to reconcile the two things.
Yeah, that's very interesting. Thank you. So Andres, I think, has a question there, maybe.
Yeah, I think it's maybe just what Carlo, can you hear me? Just what Carlo started saying, that in principle, I can get non-locality by applying renorm group, by integrating out the high frequency modes. In principle, I could just smear the field by applying heap kernel, something like e to the power xi dt square. And This way I get non-local theory in principle from local theory. And the question would be what your procedure returns in that case. Wouldn't it be in some sense reverse of renorm group? Maybe.
So this is a question for Carlo.
Well, can you hear me?
Yeah, I think it's for you, Barton.
Okay, so I'm not sure I got the question exactly right. Maybe you can repeat.
How is your when in your procedure you basically throw away field configurations with oscillations, with time oscillations with frequency higher than 1 over psi. If you take them into account, then your procedure, I think, would not work. So it must be somehow related to renorm group. In the renorm group, we integrate out or project to field configurations. Polchinski style renorm group. You smear with a heat kernel the phi, the field. I mean, if your procedure will not work if you do not throw away field configurations with frequency higher than 1 over psi.
Well, you know, this is just like effective field theory. I don't think we're doing any different than effective field theory. That
yeah. That was the question. Yes, how exactly it is related to? Well, there is a renorm group procedure. You can just
you can you could in some sense think of it as renormalization group, in which you can in that there is a way in which well, the way we think, at least I used to think of the renormalization group in this case, is in a series of transformations that change the value of psi. So you know, psi has off-shell information. You know, it's at least in the original way the theory appears, psi, you know, it appears with e to the interactions that form e to the minus psi squared, p squared plus m squared cubed. So that's a Lagrangian that depends on psi, and by field redefinitions, you can change the value of psi. Now, that doesn't mean that psi doesn't have effect. It means that you can encode the effect in more complicated terms. So changing psi is a kind of renormalization group operation, and it's a field redefinition that induces higher order terms in the action. We used to call changing the length of stubs in the field.
Yes. That's what I meant. Yes.
So, right.
It seems that your procedure goes in the opposite direction because it removes these non-localities and gives you back local theory.
But
would it be just reverse to renorm group?
Yeah, but that's only in the case of purely time-dependent thing.
Yes. At least yes.
Yeah, that's right.
You could do renorm group in that case. It's not bad.
So, but on the other hand, for the space-time dependent case, the non-locality remains. And if you change, you can change psi squared in a theory and you get an equivalent theory, but the Lagrangian changes quite dramatically. So that's a renormalization group perspective in which the scale psi then is kind of interpreted as defining a cutoff or something like that.
I could do renormalization group in one-dimensional case. I could say that other dimensions are non-existent, just time. It's not forbidden to do renorm group procedure in that
Right.
case.
So presumably that's kind of what happens if you analyze the chi-square dependence of the potential. You know, you know, it has you would think that there should be some renormalization group analysis that can give you hints as to what is the chi-square dependence of the potential, but at least we haven't quite tried to do it that way, but it would seem like a reasonable thing to try.
I see. Thank you.
There might be some RG constraints on that quantity, or some identities or something that have to be satisfied.
Mm-hmm.
Thanks. So I think we went a bit over time. So thanks a lot, Barton. So we stop the recording now. Debashish, you want to ask, or you?
Yeah. Hi, Barton. Could I ask something?
Yes.
Yeah. I was wondering about the theory that at the end, when you get rid of all the non-locality, instead of this new degree of freedom, you have a canonical kinetic term and a standard potential term.
Yes.
That is correct, right? So we can use the Noether's theorem and get a notion of Hamiltonian and correspondingly energy for this theory. How is this related to the original theory that you started with? Because there, I don't know whether the standard Noether theorem probably has some subtleties, and also I don't know how to reconcile this with the fact that the oscillations are not continuing with the redefined field.
Right. The energy is not problematic. For the energy, even the Noether procedure generalized for the non-local theory does give you a nice energy functional, and that was tested early on with Mon tested, and it's conserved in the rolling, and everything is good. So in the redefined version of the theory that we have, I don't think there's a problem with the energy. They coincide with the one of the non-local theory, and it's conserved. So the canonical expression for the energy, which is phi dot squared plus v of phi, it's okay. On the other hand, I think the pressure is not clear how to do it. For the non-local theory, the pressure calculation was done by Haitang Yang, covariantizing, coupling into the metric and varying it. Nevertheless, that pressure didn't give the answer that we expected for tachyon matter. So for the redefined theory that we have, I don't think you can use the pressure of the Noether procedure of a canonical field theory. That pressure would just give a standard thing. Would say you have the normal pressure of a D brane, which is negative, then it oscillates and comes back to the right result. So there would be no mystery there, but you're not getting the tachyon matter in that picture. So, so there's either you could try and improve. You could try improvements of the pressure calculation, but at the end of the day, presumably the right way to do this is with a boundary state. If you're doing it in theory, if you're doing it in the non-local model, maybe the non. So it could be, of course, that the non-local model is not quite good fully, and it's only good in the context of string theory. And without string theory, the non-local model is just not giving regular physics. It sounds a little strange because the solutions look very similar, but it's conceivable. But certainly the calculation of pressure and observables in both the non-local model and its redefined version are both questionable at this moment. So
that's an artifact of neglecting the other string modes. That's what you're saying?
Well, you know, if the pressure behaves very nicely with this solution with the higher modes, maybe the higher modes are responsible for it. That's, you know, I think it's a little unclear whether what is the magic of the boundary state. Is it relative to the tachyon model? Is it just adding all the massive contributions, or is it doing some sort of improvements in the stress tensor that wouldn't occur to us naively in the context of field theory? So there could be improvements to the stress tensor that change the value of the pressure, and we wouldn't know. Maybe the boundary state is doing improvements, or maybe it's just including the effects of higher modes. We just, at least I don't know which one it is.
Thank you.
Sure.
Okay, so thanks again, Barton, for inaugurating this series, and so thanks to everyone for attending. So next talk it will be in 2 weeks by Cargo. So I will send an email for the titles and more information soon. And so I'm stopping recording. People who want to hang around a bit more can stay, so I will be there. And
very good.